Okay, welcome back again to our lecture on beam stirrups. Okay, so again we have this region. We have these regions, region 1 where stirrups are required, and then region 2 where concrete alone can carry the shear, and region 3 where no stirrups are required. But again, as I've said, that even though in this region 2, even though concrete alone can carry the shear, we still have to provide stirrups. Okay, so there's gonna be a minimum spacing as well as maximum spacing. Okay, so the design of this stirrup layout or spacing or stirrup spacings would be to determine up to where would be the minimum spacings, and then up to where would be these maximum spacings will start. Okay, so even though here in section 2 it is obvious that that will that we can utilize the maximum spacing here, but actually at some portions it will start somewhere here. Okay, and also you can do um, you can do you can do increments so that um, you can farther reduce the number of stirrups. Okay, so it's something like this. So if you have this minimum spacing, and let's say you have this shear capacity, okay, and then if you have at the start of maximum spacing you have this let's say you have this shear capacity. Okay, so you can actually reduce the number of stirrups if you do increments. So let's say you do um, let's say something like this. Okay, another increment and then another increment. So in that way you can reduce actually the number of stirrups, the total number of stirrups. Okay, so now let's convert this diagram into um, to something like what we'll encounter in the drawing or in the construction. So we have this column and we have this beam, and this would be our, say, our top bar or longitudinal bar. Then at the bottom will be another longitudinal bar. Okay, so we have a minimum. Let's say we can draw this minimum spacing. Then um, okay, so let's say this is our section 1, and then let's say this is our section 2, then this is our section 3, and this will be our center line. Okay, so in section 1, stirrups are required, but then there's going to be a mixture of minimum and maximum spacing. Then here, the section 2, concrete alone can carry the shear, but we still have to provide reinforcements, and we can utilize the maximum spacing allowable. Okay, so here on the right side, it's gonna be a mirror image. Okay, so oftentimes in the drawing, what you'll see is that um, they'll specify stirrups something like 2 or let's say 10 mm rebars, let's say 10 mm bar, then 2 at 50, then 2 at 100, or let's say 2 at 150 or something, then rest 250. Okay, so what that means is we the stirrup is a 10 bar, and then the spacing, there's gonna be two stirrups at uh, at 50. Okay, so meaning, okay, so let's say this is it. We have 50 spacing, okay, 50. Then let's say we have 100, then 100, then 150 here, 150, and then the rest is, let's say, 250 or 200, depending um, upon the design. Okay, so it's something like this. Or sometimes it can be found. This notation can be found in the table or in the beam schedule. Okay, so for example, we have this beam schedule, and we have, let's say, B1, and then let's say the top bars, the bottom, something, and then we have this a column for stirrup. Okay, so let's say top bar, something like this, or if they include mid span, or I mean, if they separated mid span or the support. Okay, so that's gonna be how it is laid out in the drawing. Okay, so for stirrup, then you can also see a 10 mm, for example, 10 mm bar, 2 at 50, two at let's say 75 mm, etc. Okay, and then the rest is 250. Okay, so now let's move on to the maximum stirrup spacing. Okay, so for the S max, um, we have this criteria: a minimum of either D. Okay, so effective depth divided by 2 or 600 mm, whichever is minimum. And another criteria for uh, using this equation: AV FYT over 0.62 square root of FC prime times B. Okay, beam width. Okay, so take note that this criteria is for VS less than 0.33 square root of FC prime BD. Okay, so you can check that out in our lecture handouts. Okay, and um, so I think we'll now do a sample problem on this stirrup spacing. Okay, so for our problem number one, we have this beam section. We have a 375 mm beam width and an effective depth of 570 mm. The problem states that we have a 10 mm closed stirrups. Okay, so this is our stirrups, and it's a 10 mm rebar, an FC prime of 27.6 megapascals, an FY of 275 megapascals. The factored loads, distributed loads, 156.4 kilonewton per meter, and a length of 6 meter. Okay, so let's just say we have a simply supported. Okay, so for the first step, okay, so let's write step one. We have to construct the shear diagram, or okay, let's just say construct the shear diagram. Okay, so for the shear diagram, since we have a uniformly distributed, okay, so we have a uniformly distributed loads simply supported at a length of 6 meters, then our maximum shear here, okay, so our V max, that's gonna be WL all over 2. So if you substitute 156.4 times 6 all over 2, our V max would be 469.2 kilonewtons. Okay, so after determining this, then we have to determine the points. So the VVC, the 1/2 of VVC, because that's gonna show the regions of the, or let's say that's gonna show the shear regions along the beam length. Okay, so now let's solve for phi VC. So our equation here is the strength reduction factor times 0.17 BD square root of FC prime. Okay, so if you substitute the value, we have a 0.75 times 0.17 times B. So we have a millimeter mm in B and D. So 375 mm times 570 mm times the square root of FC prime. Our FC prime is 27.6. Okay, so if we calculate this, we get a value of 143.176 kilonewton. Now we can solve for 1/2 of PVC. So basically, that's just 143.176 kilonewton all over 2. Okay, and if you solve this, you get the value of 71.588 kilonewtons. Okay, so what else do we need? We need the value of the, let's say, the end shear reduction. So the shear at a distance d. Okay, so here you can, to determine this, you can actually do a similar triangle, or you can determine this equation of the shear line. Okay, so if you try um, let's say express that in the line equation of y is equal to mx plus b, you can actually obtain the equation of these shear lines. But since this is a straight line, then you can also, alternatively, you can also use the principle of similar triangles. Okay, so basically, if we plot this here, okay, so this is our VD, and our distance here is the distance D, which is 0.57. Okay, but the distance, the whole distance is since we have a 6 meters, then if this is just half, then that's going to be 3 meters. And this distance from this, let's say, zero shear to the maximum, this is 469.2 kilonewtons. Okay, so this is our shear diagrams. Okay, so if we do a similar triangle, we get a 469.2. Okay, so what is this? What is this triangle? Okay, so this small triangle, and then its ratio to this large triangle. Okay, so 469.2 minus v sub d all over the distance. So the distance 0.57 is equal to the larger triangle, which is 469.2 all over the larger, let's say, adjacent side. So that's 3 meters. Okay, so this is in kilonewtons, this is in kilonewtons. So the VD, if you do the calculation, you'll get a value of 380 kilonewtons. Okay, so now let's determine the X at VBC. Okay, so in order to obtain these X values, you can also, again, you can just use the similar triangles. Okay, so we have this, let's say phi. This is our phi VC, and what would be this X value? Okay, this 3 meters. Then this is 469.2. Okay, so 469.2. Okay, so the larger triangle over the adjacent, which is 3, is equal to okay, so this is our larger triangle. Then our smaller triangle is this one. Okay, so let's say this is this would be 3 minus x. Okay, so what is this VBC? This is 143.176 all over 3 minus. Okay, so if you do the calculation, you'll get an x value of um, 2.08 meters. Okay, or let's just say 2 meters. And then x at 1/2 VBC. So if you do the calculation again using the similar triangles, you'll get a value of x is equal to 2.54 meters. Okay, so this will be our values for the points. So now let's plot out in this form, or in this way, or in a graphical way. Okay, so we have the factored shear at the vertical axis, and we have the distance x, and that's in meter, and this one is in kilonewton. Okay, so this is our shear line. Okay, and we terminate here at the center line. Okay, so the maximum value that we get is 469.2, and we have a distance at a distance d. We have a value of VD is equal to 380 kilonewton. Okay, so this is it at a distance d. And then here we have shear value of VBC, which is 143.176 Okay, so that's at a distance 2 meters. Then 1/2 of VVC is equal to 71.58. Okay, and this one is 2.54, or let's just say 2.5 meters. Okay, so here now we can plot the regions here from x equal to 0 to x equal to 2. That's gonna be the region 1. Then this will be the region 2, and from 2.5 to the center line, that's gonna be the region 3. So again, the region 1 is we need stirrups, or stirrups are required. Then for region 2, concrete carries the shear, but we still have to provide steel reinforcements here. And then here, the region 3, no stirrups are required. Okay, so that's our step number 3. So now for the step 4, since we now know the regions, then we can solve for the minimum spacing. So calculating the S mean. Okay, so S mean is equal to this equation. Then VD minus VVC. Okay, so if you substitute the value, we have 0.725 times. Okay, so what is the shear area? Okay, so since we have a double leg type, then we have 2 times the bar diameter. Okay, so 2 times the area of 10 bar squared times the yield strength of shear reinforcement, 275 megapascals, times the depth, which is 570 all over, what is this? This is 380 kilonewtons. Okay, minus 143.17 kilonewtons. Okay, so take note, this is in Newton per squared. This is squared, ms squared. So we have to convert this to Newton. So if you convert that, you get a value of 77.9 mm. Okay, so in construction, we're gonna need a reasonable a reasonable value, or a practical value, that's gonna be a whole number, or let's say in an increment of 5 mm. Okay, so that's gonna be either 80 mm or 75 mm or 70 mm. Okay, but take note that if we have a narrow spacing, or a smaller spacing, we have an increased capacity, and a wider spacing means that you have less capacity. Okay, so this would be to round down. Okay, so S mean would be, let's say, 75 mm. Okay, so now since we have this S mean, then we can solve for the maximum spacing. Okay, so step 5. Okay, so S max, that's gonna be minimum of either D all over 2 or 600 mm, or another criteria, which is ABE161, over 0.062 square root of fc prime times b. So if you calculate this, if you substitute all the value, you get a minimum of either 285 mm or 350 mm. So which means that we have a 285 mm as our maximum spacing. Okay, so now that we know the maximum spacing and the minimum spacing, now we have to determine where will this maximum spacing will start along the beam length. Okay, so to determine that, we have to calculate um, our shear capacity of steel, which is ABE161 times D all over S. But of course, we have to substitute the maximum spacing, so S max. Okay, so we have 2 times our shear area, 28.54 mm squared, times 275 megapascals, times 570 mm for our effective depth, and a maximum spacing of 285 mm. So what we get is 86.394 kilonewtons. Okay, so if we take the factor shear capacity of steel, if we multiply that to 0.75, so 0.75 times 86.394, we get a value of 64.79 kilonewtons. Okay, so after that, we have to solve for the nominal shear capacity of the beam. Um, so that's going to be the sum of the shear capacity of concrete plus the shear capacity of steel. So since we already obtained a value for this, now we have just recently solved the value of this, then if you add that up, okay, plus 64.79, that's gonna be 207.9 kilonewtons. Now we'll refer back to our shear diagram. Now if our load is VVN, then what's gonna be the X value? Okay, so you can you you can just apply the principles of similar triangles, or if you want, you can obtain the equation of the shear line, and then you can solve for either the X or this one. Okay, so now since we have this and we want to determine okay, so this was the illustration for the similar triangles. So if we have this VVN, then what's going to be the location or the X location? Okay, because that's where the maximum spacing will start. So you can obtain this by similar triangles, or if you want, you can just obtain the equation of the shear line. Okay, so if you do that, um, you'll get an X value of 1.67 meters. So now if we draw our beam, example, this is our beam. Okay, and let's say this is our let's say 1.67 meters. Let's say 1.65. Let's say this is our center line, which is 3 meters. Okay, so if we label this, we have 3 meters, and our section 3, we have I think that's 2.5, and then for where the maximum spacing will start, that's gonna be 1.65 meters. Okay, so So if we lay out the stirrup, so how many stirrups um, at this at the minimum spacing will reach the 1.65 meters. Okay, so meaning that in this section we're gonna um, this will be the minimum spacing, and here we this is where we'll apply the maximum spacing. Okay, so S max, that's 285. So that's 285 mm, and then this is 75 mm. Okay, so I'd also like to point out that usually, let's say this is our 75 mm. Okay, then another 75 mm. So the first one, uh, we usually divide this into two. So 75 divided by 2, that's gonna be 37.5. Okay, so if you do the math, what you'll get is you can specify 2 at 37.5 mm, and then 20 at 75 mm, and then rest at 285 mm. Okay, so you can still improve this this design if you do um, if you apply another increment in the shear loads. So if you recall what I've mentioned, that let's say this is your loadings, your shear loads, then the spacing of the stirrups you are providing something like this, for example, then um, from here onwards, you let's say this is the maximum, S max, and then let's say this is S min. Okay, so you can further improve this if you do um, let's say another increments or more. Okay, so that will reduce the number of stirrups. Okay, so the next video, maybe I'll do another problem where there's a concentrated loads in addition to the uniform loadings, or we can move on to our next topics on reinforced concrete columns.